iterative techniques for solving AX equals B. And generally these techniques are used when n is very large. N is basically the size of the matrix or number of unknowns. N is very large, say 1,000. And we saw that one of the technique that we have learned in the last lecture is by splitting A as Q minus P, X equals B. Then we have Qx is equals to Px plus B. And then we use iteration. Where we say that start with the guess for X vector. You have different elements x1, 0, x2, 0, and so on, xn 0. And solve for x1, the first iteration. Solve for x1 vector and keep on doing so.
Professor?
Yes.
I have a question. What is the problem with n very small for this method when you have small n?
So you probably don't get any advantage of using this technique, first of all. And second thing is that these are not exact solution. For small n, you can get exact solution using Gauss elimination technique or LU decomposition, Cholesky factorization, and so on and so forth. So these are not giving you exact solutions. So when you have small n's, you would prefer to get exact solutions, and there is no other advantage you can get from the computational side of it.
Okay, thank you.
Yeah, no problem. Okay, so that's what we actually learned, and I told you that if Q's and P's are defined such that, let's say if A is D plus L plus U, and if Q is equals to D and P is equals to L plus negative L plus U, then what we have is called Jacobi method. Then the technique is called Jacobi technique. Jacobi's technique. Okay, that's what we did in the last lecture. Any questions, guys, on this so far? So we actually also took one specific problem from 11.24 example, the solved example. So I'm just retaking or redoing that. I mean, using the same matrix for A. So A was split as D plus L plus U, and you guys know what D matrix is and what L matrix is. So D is basically 4, 0, 0, 0, 5, 0, 0, 0, 6. L matrix would be 0, 0, 0, zeros, 0, zeros, by negative 2, 2, and 1. And your U matrix would be 0, 0, 0, 1, negative 1, and 0. Okay, so if instead of using Q as D and P as negative L plus U, if we take Q as D plus L and P as negative U, Then what we have, we call as Gauss-Seidel technique. Okay. So everything remains the same, how to solve the system of equations using iterations. Now this system of equation also only works uh, when we have a strictly diagonally dominant matrix, or basically the convergence. I mean, this technique will only work when this matrix A is strictly diagonally dominant. A has to be SDD form. SDD means strictly diagonally dominant. Can somebody volunteer what is strictly diagonally dominant means?
It's that the um, diagonal is the highest value of the
Yeah.
rows.
So not the highest value diagonal,
The highest added value of
It's
the row.
greater than the sum of the.
yeah, it's greater than the sum of the absolute value of all the other entries in the row. So you sum all the other entries, I mean, absolute value of the other entries, and it has to be less than the absolute value of the diagonal. That's what your diagonal dominant is. So this technique is guaranteed to converge only in these specific cases. And as I said to you, that if Q is equals to D and P is equals to negative L plus U, then you use this form. I mean, you substitute Q as D here and P as negative L plus U here. You keep on solving them. Then what you call as Jacobi technique. And if you use, instead of D, if you use D plus L, which is this plus this, if you use Q as D plus L and P as negative of U, which is negative of this, we call as Gauss-Seidel technique. So we saw this Jacobi's technique in the last lecture, or how it works. So here I'm just going to rewrite these equations, I mean this matrix system in equation form, to show that what actually advantage we will get by putting Q as D plus L instead of just D. So I'm just going to rewrite this matrix in an equation form, and then hopefully it will be clearer. So if I rewrite this matrix, so it will be 4x1 plus x2 negative x3 equals 1. Then I have negative 2x1 plus 5x2 is equals to negative 7. 2x1 plus x2 plus 6x3 equals 13. Is everybody with me so far?
Yes.
Yeah. Great. So now what I'm doing, just as I did in the last lecture, I'm going to solve for x1 from the first equation. So when I do that, what I will get is x1 is equals to 1 divided by 4, negative x2 plus x3 plus 1. And I use iterative technique. So I will say this is k plus 1th iteration, this is kth iteration, this is kth iteration. Similarly, from the second equation, what I will get is x2 for the k plus 1th iteration is 1 over 5, 2x1 for the k plus kth iteration, negative 7. And then from the third equation, x3 for the k plus 1th iteration is 1 over 6, negative 2x1 k1 minus x2 for the, sorry, not k1, it's kth iteration, x2 for the kth iteration plus 13. Is everybody following what I'm saying or doing here?
Yes, Professor.
Yeah, if you
Yes.
refer your notes from your last lecture, you will probably see that's what we have done, right? Everybody is with me?
Yes.
Great. So what we are doing, this is what we have known as Gauss-Seidel technique. Now, not sorry, Jacobi technique. Now, what is different in Gauss-Seidel technique is, if you look at this first equation, if I know x2 and x3, I solve for x1. That's what I'm doing in basically. I'm actually guessing for the previous time step and previous iteration value. So while solving for this, I already know what is x2 and x3, because this is for kth iteration. For, let's say, if k starts from 0. So this is for first iteration. I already know what my values x2 0 and x3 zeros are. I can solve it for x1. Is everybody getting what I'm saying? If not, say when we start the iteration, is I say that we start with 1, 0, -1. That's assumption. I can take any vector as I like, but I will start with this, let's say. So I know what is x1, 0, what is x2, 0, and what is x3, 0. And I want to calculate x of 1, which is means I want to calculate x of x1 of first iteration, x2 component for the first iteration, x3 component for the first iteration, right? And that's what I'm going to do using these equations. Is everybody following what I'm doing?
Yes, Professor.
Yeah. And this is basically x1 for the 0th iteration, x2 for the 0th iteration, x3 component for the 0th iteration. This is what it is. This is your guess vector. That is the first guess. And that is a guess. You can take any guess. I'm just using this. You can use 0, 0, 0. You can use 1, 1, 1, whatever you would like to choose. Whatever, that's up to you. The reason it will work because our A matrix is strictly diagonally dominant. That is why any guess of x zeros is going to lead us to the actual solution. So that it is independent of the initial assumption. So for example, you assume this, that means for the 0th iteration, you have got these values. Now if I need to find out what for the first iteration, what should be the values of individual components, I use this equation, right? So I plug in the values of x2, 0 and x3, 0 here, and I will get x1, 1. Similarly, I will get x2, 1, x3, 1. Yeah? Is there
So far.
Yeah?
Yeah.
Now you see that after this, after solving for x1 for the k plus 1th iteration, when I come back to here, now I am still using x1 for the kth iteration. If I can change this for, instead of k, I use is k plus 1. That means I'm using the current value. Instead of using this, I use the current value of x1 because this is already solved, right? When I'm solving for x1, k plus 1, so I use this. Now when I'm solving for x2 component, the second component of x vector at k plus 1th iteration, I no longer need the value of x1 for the previous iteration. I can use the current iteration because I have already solved it here. So if I select k, if I change the k to k plus 1, then that it becomes your Gauss-Seidel technique. Similarly, when you solve for x2 k plus 1 and you are now coming to solve for x3 k plus 1, then instead of using this, you can, all the previous k plus 1 current iteration values can be selected from that has been solved. Does it make sense to you guys?
Yes, Professor. So this technique is basically is faster than the previous one.
It will be faster in convergence. It will be more fast. You will actually converge to the actual solution more faster because you are taking current values of the components which are available. So at this point, I do not have the values of x2 and x3 for my current iteration. Current iteration is k plus 1th iteration. So if k is 0, so if I have to find x1 for the first iteration, I'm using x2 for the 0th iteration, x3 for the 0th iteration. I do not have the values of x2 and x3 for the current iteration. So I use the previous values. But when I'm solving the second equation, at least for x1 and any component that is coming before the x2, so before x2, only x1 comes. So I already have solved for x1 for the current iteration. So instead of using x1, 0, I'm using x1 for the first iteration. So from this. Does it make sense?
Yes. And another thing is the initial guess. Any change that the initial guess not convert to the exact solution.
No, because this is strictly diagonally dominant, it is always going to converge.
Professor, I have a quick question as well.
Yeah.
Say, for example, in the x2, you can use the x1 k plus 1. If there was an x3 in that equation, would you use the x k xk, or would you?
Yeah, for if there would be x3 here, I would only use x3 of k, no, because I don't have the value of k, x3 k plus 1 in this.
Okay, so it's when you can plug in the plus one, you do.
Yes, yes.
Okay.
Whenever you can plug in the current values, you plug in there. So here you cannot plug in those current values. So you have to use the previous values. But here you can use the current value. And here you can use the current values as well. So use the current values basically. Make sense, guys? This
Yeah.
matrix form is basically the same thing as we are doing here. So Q is D plus L and P is negative U. So I'm not showing you explicitly here. You can do it yourself, but this is, if you use Q as only D, then I'm only using current iteration. I'm using previous iteration values. K is X1K, X1K, X3, X2K, everything will be on the right-hand side. Everything will be from the previous timestamp. But if I use Q as D plus L, then on the right-hand side, all the available values from the current iteration can be used. So that is what the difference is between Jacobi's and Gauss-Seidel technique. So when you are doing coding in MATLAB, you don't need to worry about these specific notations. You just use this specific algorithm where you know what is Q, you know what is P, because Q is your D matrix, P is your L plus U, that is your Jacobi. And if you have to use Gauss-Seidel, then Q will be D plus L and P is U. That's it. But when you actually look for the meaning behind that, and what is happening inside, so this is what we are actually doing in Gauss-Seidel technique. Make sense, guys?
Yes, 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 yes.
Any questions so far?
At this point, Professor.
Okay. So that basically completes our discussion on the matrix solution of equations. The next topic is about Newton's technique for nonlinear system of equations. So far we have done for linear. Technique for nonlinear system of equations. Okay, so if we have a system of equations like f1 x y equals 0 and f2 of x of y equals 0, and they have to be solved simultaneously. You can have more than that as well. Need to be solved simultaneously. Simultaneously. Okay. So for example, so far what you have seen that if you are given only f of x equals 0, you know how to basically solve for that. So you know that you can use bisection method, you can use secant method, or you can use Newton-Raphson method, or maybe fixed point iteration method. But if you have a system of equations with multiple variables and you need to solve them simultaneously, how to solve for that? For example, I can select, say, for example, f1 of x of y is sine of x plus x squared minus y. And f2 of x and y is x cubed plus 3x squared plus 1. Actually, to make the life easier, let me actually use sine of x plus y squared. Okay, so let's say this is the form you have for functions, nonlinear functions. Of course, these are nonlinear functions for sure. And you would like to find a specific value of x and y that actually satisfies both these functions, or we basically solve for both of these functions simultaneously. So when you have to do this, or you have to find the solution for that, what you can do is you can basically use Taylor series expansion about the actual solution. So let's say x2, y2 is the solution for the given system of equations, okay? This is the solution for given system of equations. If that is the case, then if I select actually selecting x2 minus x1 as delta x, and where x1 and y1 are the 2 points which is close to your actual solution. So if I actually expand in Taylor series, what I will get is f1 of x comma y with x2 y2 will be f1 about x1 y1 plus x2 minus x1 del f1 by del x derivative with respect to x at x1 and y1 point plus y2 minus y1 times derivative of f1 with respect to y at x1 and y1 plus higher order terms. Is everybody getting what I'm doing here? So I have a nonlinear system of equations, and there are multiple variables, x and y. It's not a single variable. There are more than one variable. And you need to find a solution for that. That is, you need to find a value of x and y, which I'm saying x2, y2, that satisfies both of them. That satisfies both of them means f1 of x2, y2 is 0. It basically means f1 at x2, y2 is equals to 0, and f2 at x2, y2 equals 0. Okay. So if x2, y2 is the solution, that means it satisfies both of these conditions simultaneously. So the same point satisfies this function and it satisfies this function. Are you getting here? Guys, what I'm doing?
Yes.
Professor, if there's supposed to be a solution, wouldn't you set them equal to each other?
That's what we are actually trying to do. We are basically trying to set it equal to each other, and that's also saying that they are also satisfy this specific equation.
Okay.
Sorry, you have a question? Go ahead.
Oh, no, I did not, Professor.
Oh no, that was it. That was the only question I had.
Okay. So what is the left hand side? X1, yeah, x2, y2, not x1, y2. It is x2, y2. And since I'm saying that this f1 x2 y2 is going to be 0 because x2 y2 is actual solution, so that means this term is 0, and I have here f1 x1 y1 plus delta x del f1 by del x at x1 y1 plus delta y del f1 by del y at x1 y1. I am neglecting all the high order terms, and what I'm doing here, I'm trying to solve this system of equation, which becomes del f1 by del x del f1 by del y del f2 by del x del f2 by del y times delta x delta y should be equals to negative of f1 and f2 at calculated at x1 y1. So this specific matrix is called a Jacobian matrix. And you can solve this assuming that Jacobian matrix, the determinant of this matrix is not equals to 0. It is not singular. So then only you can solve for delta x and delta y. And then what you do is for the first iteration, you actually take the value, you actually assume the x1, y1, which is near to the root, actual root. But then you said x2, the second iteration, it will be x1 plus delta x, and y2 is y1 plus delta y. And you repeat the steps of solving for delta x and delta y thereafter till the convergence. Repeat the solution steps till convergence. Let me know if it is making sense to you or not.
Professor, I have a question.
Yeah.
What did you say about this last part that you wrote, x2, y2, and then repeat the solution? I didn't catch on to it.
So, okay, so x2, y2, we assumed as the actual solution, right? And that basically satisfies this equals 0 and this also equals to 0 simultaneously. It is not that it is x2, y2 is independently satisfying this solution. It is also independently satisfying this solution. So we actually then, since we do not know what our x2, y2 is, our actual solution is, then what we do, we actually say that we guess x1, y1, which is near to the actual solution. So we do not know where the solution is, but assuming that we are guessing the values of x1, y1, which is near our exact solution, we do a Taylor series expansion and find out what will be the increment in x1 and y1 should be such that it becomes more and more closer to the actual solution. So since we solve for delta x and delta y, we add to our original estimate. This is our initial estimate, x1, y1. Then for the second iteration, we get x2 as x1 plus delta x. Now this will not be the same as this because we have neglected all the higher order terms. So our delta x will not lead us to the actual x2. So let me actually say these are exact. How should I make a distinction here? So this x2, y2, let me actually say this is bars. So that basically means these are the actual solution. In fact, I didn't need that, but still I can make a substitution here. So you see here, x2 is what? x1 plus delta x. So if your delta x is the actual, is actually, if it is taking the all the other terms and you have calculated delta x, then you can add delta x to x1 to get x2. But now what I'm saying, I'm doing is, since I have canceled all the higher terms, my delta x will not be exactly close, making it equals to x2. It will be making it closer to x2, basically. So just for an example, assuming that, say for example, x2 is 5.5, just for the sake of understanding, let's say x2 is 5.5. The actual solution 5.5 and y2 is 4.0. That's your actual solution. Now you took x, since you do not know it, but if somehow from the nature of the problem, you know that your root lies somewhere closer to this, and you start with x1 as 5 and y2 as 3, then you basically calculate delta x and delta y using these equations, where this equation is basically formed using this matrix. This is your function value at x1, y1, because x1, y1 is already known to you. You already have guessed that. So you can solve delta x and delta y. Once you get delta x and delta y, what you are going to do, you are going to add it to your x1 value here. So your actually delta x, if it comes out to be 0.5, then it becomes equals to x2. But generally delta x will not be equals to 0.5. It will be somewhat near it. Let's say delta x comes out to be 0.3. So you add that to x1, and for next iteration, it becomes you becoming more closer to your actual solution. Does that make sense?
Yes.
Yeah.
So these are all hypothetical numbers. It doesn't have any resemblance to the actual values, but I'm just picking these values just to make sure that you understand the process here, what we are doing.
Yeah. So if I could reiterate, Professor.
Yeah.
So so we're solving for the delta x and delta y that gets updated
Yes.
for the, and then once it reaches the tolerance set, that's when it breaks.
Yeah, and the tolerance is given by this norm, where the norm is your x and y vector for the k plus 1th iteration step minus x and y vector for the kth iteration step has to be less than the tolerance value.
Professor, I have a question.
Yes, go ahead.
How did you get delta x equals 0.0 and 0.03?
So I have solved using this matrix equation. So here, this Jacobian matrix is what? It is basically derivative of f1 with respect to x, evaluated at x1, y1. So what is derivative of f1 with respect to x? If I see this derivative of, let me actually do that. So derivative of f1 with respect to x would be what? It will be cosine of x, right? Derivative of f1 with respect to y would be what? 2y. Derivative of f2 with respect to x would be what? 3x squared plus 6x. And derivative of f2 with respect to y would be 0. So these are the derivatives which I'm going to use here and evaluated at x1, y1. So already I'm knowing x1 is 5 and y1 is 3, which is the guess. This is the initial estimate. So I use these values x1, y1 and plug in this. So you basically have this matrix, Jacobian matrix time delta x, delta y, which is your unknowns. And you solve for the right-hand side vector, which is already known, f1 at evaluated at x1, y1. So what will be the value of f1 by substituting x as x1 and y as y1? You can get f1. And that is what you are plugging in here. So everything is known except these unknowns, delta x and delta y, that needs to be added to your increments.
So
yeah,
point x1 and y1, that again is an arbitrary point that is just a starting point, right? It's going to be.
Yeah, it is a starting point and it is a guess. You are guessing that basically.
Okay.
So I'm just looking at the any solved or any specific. So do you guys have the textbook with you right now?
Yes.
Yeah. So can I ask you to look at example 11.31? Solved example 11.31. Have you opened that specific example? I just wanted you to actually look at the functions that are given f1 and f2 that are defined, and what actually, as one of you are pointing out, I'm just actually thinking if it is visible in the document camera. So if you look at page number 409, you will actually see that this is your basically two functions, and you are, when you're doing it, solving it simultaneously, you are basically finding the intersection of these two functions. So these two functions, one of these functions basically represent a curve or is an equation of a curve in X and Y coordinates. So if you look individually F1 value or individual F1, this is your individual F1 function equals to 0. This is basically an equation of a curve, and similarly it is an equation of a curve as well. So you are plotting the curve and you are trying to find the intersection of these two functions, and that is what your actual root is. So root of that, when you're solving the system equation simultaneously, so you are basically trying to find a point which is satisfied by both the functions and simultaneously. So that is a point where which satisfies both f1 equals 0 and f2 equals 0. Does that make sense?
Yes.
Yeah.
Yeah, I could see it.
Yeah. So that is what basically what one of you actually pointed out. I missed the name, that you need to basically equate it. You may need to equate that, which we are actually doing. We are doing it simultaneously, and any point in this curve and in this curve satisfies that equation, that f1 equals 0 and f2 equals 0. That is what this curve represents. And when they intersect, that means it is a common point which satisfies both f1 equals 0 and f2 equals 0 simultaneously. And that's what we are trying to find out by the technique. Does it make sense?
Yes.
Yeah. Okay, any other question, guys?
This method, professor, only works with two equations or so?
Sorry, come again?
So this method only works with two equations then?
No, it can work with any equation. Then if you have f3 as well, then you will have the Jacobian will be 3 by 3. Then you will have del f1 by del x at x1 y1 z1, del f1 by del y at x1 y1 z1, and del f1 by del z at x1 y1 z1. So you will have a 3 by 3 matrix. So here you have partial derivative of f1 with respect to x, with respect to y, and if there is a third dimension, you will have with respect to z. And it will not only be just okay, so I believe what your question was that whether you can have it with f3, right? That's what you were saying?
Yes.
Okay, so I was basically mentioning your x, y. I mean, you have more number of vectors, unknown vectors, x, y, and z. So if you have more number of functions to be simultaneously solved, which I'm just thinking, is it the solution may lie or may not lie? I mean, it is very hard to see that the two functions or three functions are intersecting at the same point, which is hard to visualize actually. So let me actually think on that and come back to you, because at this point I'm not having the correct answer in my mind, because to me it seems that you want to find an intersection of three functions and they all are intersecting at one point, which is very difficult case or very rare case where you have three functions or more than two functions which are intersecting and they are intersecting at one common point. So
Also, it's going to be like, I guess, least squares method for just for multiple variables, I guess.
yeah, you can basically find out, yeah, least square, because then it will be more number of equations. Yeah, you are right. You have more number of equations and less number of unknowns. So it will be non-linear least squares technique. Basically, it will not be just the linear least squares, it will be non-linear least squares. So that is even, I mean, their solutions exist, but it needs to be, I mean, I don't have the ready reference in front of me. I have to review it and then I will let you know how to solve for that.
Thank you.
Yeah.
So Professor, in example 11.31, so when you set the two equations equal to each other, the solution of both the values that you solve for x and y will automatically go to 0?
Yes. Yes.
Okay.
And see, if I'm just looking at this, you have what would have been a linear system of equation. You basically say that, okay, y and x are basically linearly related. So if I say y is equals to ax, ax square plus whatever polynomial, so f of x. So this specific is equation, or this specific, okay, let's take a very simple case. Y equals sine x, let's say. Okay, so this is again a function of x and y where the function is sine of x minus y equals 0. Right? And that's what you are plotting. Y is here, x is here, and you are basically plotting sine for every x, whatever the y is taking. That's what it is doing. And let's say the other function, this is f1. And let's say another function is y equals to x. This is f2. f2 of x of y is basically y minus x equals 0. So another function is this. So these are basically, you have linear in y, but non-linear in x. But here you will see that these are linear, basically non-linear in both y and x. Do you see what I'm saying? If you
I don't understand what you're trying to say by that. What are you trying to say by that?
So what I'm saying that if you actually find this intersecting point, then this point will automatically satisfy this equation and this equation, where both of them are going to 0.
Got it. All right. Thank you.
Does it make sense?
Yeah.
So even if f1 is not, I mean, if this is the point where they are intersecting, and this point actually satisfies this separately 0 and this separately 0.
Got it.
Thanks.
Professor, just to add on to that, so if you were given, say, a range where you only want certain possibilities for the value to be satisfied, say like in a code, you would have to specify only do between these boundaries to find your solution?
Yeah. So that is what you will basically need to know, how to use x1 and y1, because your convergence, you actually may not even converge, but the convergence will depend on starting values. So the starting values have to be near the root, near the actual root. So if you do not know where the exact solution is, what happens that you need to first plot the functions and see where they are intersecting. So you don't know exactly at what point they are intersecting, but actually you know that this is between 4 and 5. So you know that they are basically intersecting 4 and 5. So you can basically take x as 4 and y as some number. So you can basically plot it first and see at what range they are intersecting, and then use them as starting values.
Yeah, that makes sense. It's an easier approach.
Yeah. So basically you need to graph it and see whether they are intersecting or not intersecting. And find the x1, y1, the starting solution, starting estimate, very, very close to your exact solution. Okay.
Yeah, thank you.
Are you guys getting what we are doing or what we are trying to do here? I'm asking everybody in the class.
Yes.
Yes, Professor.
Yes.
Yep. Any questions so far? Okay, if there are no more questions, then we will solve, or I mean, we will not solve, we will stop at this point today. There is only one topic that is about ill conditioning matrices. I guess you can study it. I mean, this is basically just one section in the textbook. I think you can read it by yourself, and there will be one homework problem on that topic as well. So just I left it as a homework for you to read it yourself, that section.
Topic again, Professor?
Ill conditioned matrices. So I'm asking you guys to read the section about ill conditioning, ill conditioned matrices. And basically, let me actually just give you a summary. Ill conditioned matrices are defined by a condition number of a matrix, and condition number of a matrix is given by the norm of the A matrix and multiplied by the norm of the inverse of that matrix. So if I have a matrix A as, let's say A as 2, 1, negative 1, 1. So what is the norm of A? Norm of A, basically you can start with the L2 norm. There can be many other norms as well. But L2 norm is, you actually take the square, sum square of each element, sum them up and square and take the square root. So can somebody tell me what will be the norm of this A matrix? L2 norm of this A matrix. Can somebody let me know what would that be? And similarly, taking the inverse of that and finding the L2 norm. You multiply that value, you get a condition number. So if the condition number is very, very large, then you have an ill condition matrix. Now that's a summary of that section, but I left that section to read by yourself. Matrix is ill condition.
Professor, I have a question with the, so when you have a side function and the line, you have three intersections. So depending on your initial guess, you will get.
Yes, you will get different solution depending on which value your initial guess you are taking. So if your initial guess is near this root, then you will exactly converge to this root. If you are actually near this root, you will actually converge to this root. There is no way you can get all the roots by only one estimate or one starting point.
Okay.
Yeah. Okay, guys. And you can find the L2 norm of that will be 2 square 4 plus 1, 5, 6, and 7. It will be square root of 7. And I don't know what the inverse is, and then taking the square root of that. I mean, that will be the number. So you can find that out. If you have a MATLAB, you can easily find that.
Oh, sorry. So back to that problem again. So if I given that equation, that system of equation, do I know like how many roots, how many total roots in that system?
You cannot find, or you cannot know in advance how many total roots are there unless you plot it, or you know by advance that okay, these are the roots you're expecting for it.
Okay, so if I have a plot, then I will know the total roots. Okay.
Yes. Yes.
Thank you.
Okay, guys. So if you are understanding, I mean, I left this specific topic for you to read by yourself. This is just, you can read in from the textbook, and this will basically complete chapter number 11, which we have been doing it for last 1 month. But I believe that there are many things that you can easily carry it forward. The reason we are taking so much time in this because it involves a lot of matrix computations, and many of the systems that we are going to learn or see in the remaining portion of this course will involve a little bit of matrix computation as well. So we will start with eigenvalues. and solution of eigenvalues and how to compute eigenvalues from the next lecture next week. But yeah, for chapter number 11, this is basically we are completing it, and I will ask you to do the problems by yourself if you have the time. And as I said, I'm going to post the homework number 2 soon during this weekend. Okay.